This is Ellen Pekarsky. I am recording a video about power functions, exponential functions, and logarithm functions. I'll throw in a couple more functions in there that are essentially they're just exponential functions with real-world application properties to it. So let's go ahead and get started. The first one we're going to look at, and you guys hopefully will have a copy of these notes, is your power function that is growing. And the most important things you need to know is that as what causes it to grow, and then your B value. The B value is what's going to cause it to grow, or your growth rate or whatever. And in this case, for your power function to be a growth, your B has to be greater than 0. Okay. Your graph for power function, a growth power function, is going to look. It can look like this. If it's greater than 1, it'll look like this. It'll be increasing very sharply like that. If it's a fraction or a decimal between 0 and 1, then it's going to be going like this. Okay. The initial conditions for your y-intercept are your origin. You're going to start at your origin for power functions. Okay. And then the end behavior, as x approaches positive infinity, your y is also going to approach positive infinity. So you're going to be, basically it's the right side and you're going to be going up. Okay, so now let's look at our next power function. Now this one is decay. So make sure when you're taking these notes that you look at the top left corner where it says growth or decay, so that you have it on the right side. Notice your power function equation is essentially the same. You have some number a here times x raised to another number. Okay, and with decay, your b value is going to be less than 0. Okay, and as we get into exponential functions more, we'll talk about what negative exponents do to your functions. Okay, your graph for that is going to look like this. On the left side, you're starting way high up at positive infinity, and you're decreasing the whole time. And notice that we're approaching an asymptote at your x-axis, so y equals 0. All right, so your initial y-intercept is undefined because you have a vertical asymptote here at x equals 0, and you end up with a horizontal asymptote at y equals 0 as well. Okay, your end behaviors. On the right side of your graph, your function, your y value is getting closer and closer to 0. All right, before I move on to exponential functions, I want to show you some of the variety you can have with power functions. So notice all of these are your b value is greater than 1, and if it's between 1 and 0, you just have this little branch. You've got a quadratic here. You've got, again, you have a decimal, so you're missing this left side. And then if you have an odd number, it's going to look like this. So you'll find that power functions cover a lot of different types of regular parent functions that we've seen in the past. All right, so let's look at when your b value is a decimal between 0 and 1. All these different graphs are different setups of what your power function can look like. And then we have a few more when your exponent is negative, you end up with rational functions. Okay, that's something that you probably want to take note of. Negative exponents on your power functions give you rational functions. All right, let's move on to our exponential functions. Again, make sure you are looking on the side that says growth. Okay, this is your basic formula for your exponential function. You have a leading coefficient a times some number raised to the x power, and this time your variable is the exponent. Okay, so there's two different formats you can have. You can have it like this, where b can be any number, or you can have it like this, where e is a natural number. It's kind of like pi, where pi is 3.14. E is a number, and I want to say it's like 2 point something. Don't quote me on it. We'll look at it in class. Okay, and then your a is just a leading coefficient. All right, so what makes it grow? Okay, your b value, for it to be growth, your base number here has to be greater than 1. Okay, we really aren't going to get into K, so just don't even write that down. Your graph for exponential growth is always going to look like this. It's going to have an asymptote here at y equals 0. So your horizontal asymptote is y equals 0, and so you'll approach the x-axis here, and then you'll intersect. Notice that your intersection is whatever your a value is. That tells you your y value for your y-intercept, and then it's going to shoot up really high. So I think we just went over that. Your y-intercept is 0, whatever your a value is, your leading coefficient. And then I noticed on this one they did not explain what happens on the left side of the graph. Please go ahead and write it down. As x approaches negative infinity, y is going to approach 0. Okay, and then on the positive side, on your right side of your graph, x approaches positive infinity, y is going to approach positive infinity. All right, now let's move on to exponential decay. Make sure it says decay, or I think it says decrease function, I think. So exponential decay, notice your same formula here. You have your a, your b, or a and e value. And remember, e is a number like 2 point something. Okay, so what's going to cause it to decrease this time? Anytime your base number is a number between 0 and 1. So actually, they should not have this part here because e is 2 point something, and so you can't have a decay with the e. But notice that the k value is here. So I guess I'm trying to think. You might get a decay there with the e, but yeah, you're not going to see it very often. All right, let's look at our graph. This time, we're on the left side, we're starting up way high up at positive infinity, and we're decreasing the whole way, and then we're going to approach our horizontal asymptote at y equals 0. And then your y-intercept is at whatever your a value is. Okay? That's super, super, super important to know. Please don't ever forget it. Your leading coefficient tells you your y-intercept. All right, and then on the right side of your graph, you're approaching 0, left side's approaching positive infinity. All right, so let's look at some application scenarios that you might see. You might see something that's called logistic growth. And basically what happens is, let me just go ahead and show you the graph, and then I'll look at all the formulas. Okay, so it's going to kind of grow like an exponential function, and then it's going to hit some ceiling here where it can't go past the ceiling. Okay, some examples of that is like the growth rate of humans. Nobody keeps growing all their lives. Eventually they're going to get to their maximum height, and then they're going to just stay there. Okay, so this is called an example of a logistic growth function. In this case, your C is the limit to how high you can go. All right. Your y-intercepts. Oh my gosh. So let's go back to the equation. Notice your a value is the number you're multiplying by e, or you're multiplying e by, and so usually that'll be a 1, but every once in a while you'll get a different number there. And then whatever your c value is divided by 1 plus your a value will give you your y-intercept. And then on the right side of the graph, your limit or your y value, your y is going to approach whatever your c is, okay? We will look at a couple of application problems with that. Here's another one that's called the law of cooling. It is a exponential decay, and I will, when we get to this application problem, I'll explain what all these letters stand for. The biggest thing to remember, I guess they explain some of it. So T of R is your room temperature. T sub 0 is your initial temperature. So let's say you have a cup of hot coffee. Then the temperature of that coffee when you first pour it into the cup is your T sub 0, your initial temperature. And then usually the room is not as hot as your coffee. You'd leave your coffee sitting on the table, and then what this does, this graphs the temperature over time of like your hot drink. Okay, so in this case, your limit here is your room temperature. Go ahead and sketch those, and then the y-intercept is whatever your initial temperature is, okay? And then on the right side of your graph, your function is, your y value is just going to approach your room temperature. All right, so last, I think this is the last thing, yes, logarithmic functions. I'm going to have to pull up my calculator in a little bit for this. This one, you guys will have to fill this top part stuff in. This is your basic log function, and you can see it in two ways. Some letter A, your leading coefficient, times log base B rate of x. Okay, the ln is, remember that e value from your exponents. Let's see, does this have the e value in it? Yeah, your e value here from your exponential function. So if you have a log base of e, you would write that as natural log, the ln, okay? And your b value here, your base number, it could be, there's a lot of variety on what it can be, and we'll go over that in just a second. All right. So what causes your logarithmic function to grow? It's actually the A or the B can affect your growth rate. Okay, and we'll look at that in just a second. Notice on here I don't have a graph. The reason why is because I want to show you the graph on my calculator. So here's our graph. And this time for this, your A value, your leading coefficient is just 1. And we start off with our B value being 2. Now, I'm going to show you what happens. Go ahead and sketch this graph on your paper, and then I'm going to show you what happens as you change A. So as A increases, you get a sharper curve or a higher growth rate here, okay? And it can go pretty steep, all right? But notice if it's 0, you just have a flat line, and then if it's negative, it reflects over the x-axis, okay? And does the same thing. So you could have a negative or a positive A value. Most people or most teachers won't show you that you could have a negative A value, but you can. All right, and then let's look at the B. So with B, as B increases, it actually causes this line to go lower, okay? And a couple regular or bases that you'll see most often are a 10 or a 2, and sometimes you have log base E, okay? But let me show you what happens, okay, when you get a 1. It just disappears, okay? What happens when you have a 0.1? Another reflection, the same type of reflection that you had here, or kind of the same type of reflection that you have here. So when your base number is a decimal or a fraction between 0 and 1, it flips over. And then if it's 0, it disappears again. And if it's negative, notice nothing's happening when my base number is negative. So what that tells you is that you've got an asymptote here, okay? So let's go back to the notes. Okay, so your, oh shoot, I totally messed this up. Oh, this is your, you have an asymptote here, okay? So notice, why is that selected? There we go. Notice here, this is going to be the domain. It goes from 0 to positive infinity, and notice I have a parentheses here, and the reason why I have that parentheses is because you have an asymptote at y equals 0. So you have an asymptote there. X equals 0. Sorry, I heard what I said. So you have an asymptote at x equals 0. It's a vertical asymptote. You're not going to have anything on the left side of your graph. Okay, so your end behavior, as your x value gets closer to 0, your y value is going to approach negative infinity. And then as x approaches positive infinity, so your right side of your graph, y is going to approach positive infinity as well. And what affects how fast it approaches that is your b value. So the bigger the b value, the slower you go up. All right, so that was a lot of notes. That's all the different graphs that we're going to have for this unit. It's going to be power functions, exponential functions, logarithm functions, and then we'll have a couple other functions just to throw in there for application problems. All right, see you later.